Good day, everyone. I am Jamaru Sabanal. I am going to discuss chapter 7, which is the first order circuit. So first, what is a first order circuit? A first order circuit is a characterized by first order differential equation. This is the source-free RC circuit. A source-free RC circuit occurs when its DC source is suddenly disconnected. The energy already stored in the capacitor is released to the resistor. As you can see here in the diagram or the figure, this is an example of a source-free RC circuit. Our objective is to determine the circuit response, which, for pedagogic reasons, we assume to be the voltage Vt across the capacitor. Since the capacitor is initially charged, we can assume that at T is equal to 0. The initially voltage is V0 is equal to VO, this formula, with a corresponding value of the energy stored as W0 is equal to 1 half CV squared, and here is 0. The source-free circuit, applying the KCL at the loop node of the circuit in the figure 7.1 yields, this formula will be used, or we get. So we will integrate both sides, we will get this formula, and where is the integration constant, thus this formula will appear, we get. But from the initial condition of VO I0 is equal to A is equal to V0, hence this formula or equation formula will be given. This shows that the voltage response of the RC circuit is an exponential decay of the initial voltage. The natural response of a circuit refers to the behavior in terms of voltage and current of the circuit itself with no external sources of excitation. And this is an example here, the figure 7.2. This is the example of the voltage response of the RC circuit. The rapidity with which the voltage decreases is expressed in the term of the time constant denoted by the lower case Greek letter t, like letter t or tau. The time constant of a circuit is the time required for the response to decay to a factor of 1e or 36.8% of its initial value. This implies that at tau is this formula, or tau is equal to RC. In terms of the time constant, we can use this Vt is equal to Vo e negative t over tau. If it is the power dissipated in the resistor, it will be this formula, which is Pt is equal to VIR is equal to V squared O all over Re negative 2t over tau, while the energy absorbed by the resistors up to time t is this formula. Notice that as t infinity, WR infinity, where 1 half CV squared 0, which is the same as the WC 0, the energy initially stored in the capacitor. The energy that was initially stored in the capacitor is eventually dissipated in the resistor. So now we will proceed to discuss the source-free RL circuit. So our goal is to determine the circuit response, which will we assume to be the current or IT through the inductor. We select the inductor current as the response in order to take advantage of the idea that the inductor current cannot change instantaneously. At t is equal to 0, we assume that the inductor has initial current IO, or this sorry, this one. IO is equal to, I0 is equal to IO, with the corresponding energy stored in the inductor as W0 is equal to 1/2 Li squared 0. And this figure here, this is an example of a source-free RL circuit. So applying the KVL around the loop, so this will be the formula we'll get. And rearranging the terms and integrating, it gives us this. And if taking the power of E, we have this one. And if it is constant for the RL circuit, is tau is equal to L over R. Thus, IT is equal to IO E negative T over tau. And the power dissipated in the resistors is P is equal to B, or I is equal to I squared O R E negative 2T over tau. The energy absorbed by the resistors is these formulas here below. And then this is an example of the current response of the RL circuit. And we should note that as T to the infinity, WR to infinity into 1/2 Li squared and 0, which is the same as the WL0, the initially energy stored in the inductor, as in equation 7.4. Again, the energy initially stored in the inductor is eventually dissipated in the resistor. So now we will talk about singularity functions. So singularity functions, or also called switching functions, are very useful in circuit analysis. They serve as good approximations to the switching signals that arise in circuits with switching operations. They are helpful in the neat, compact description of the some circuit phenomena, especially to the step response of RC or RL circuit, to be discussed in the next section. By definition, singularity functions are functions that either are discontinuous or have discontinuous derivatives. The three most widely used singularity functions in the circuit analysis are the unit step, the unit impulse, and the unit ramp functions. So first is the unit step functions, or U times t, is 0 for negative values of t and 1 for positive values of t. And this is the mathematical terms. And in the figure below, this is the example of the unit step function. So next is the unit impulse function. Is 0 everywhere except at t is equal to 0, where is undefined. Impulse currents and voltage occur in electric circuits as a result of switching operation or impulsive sources. Although the unit impulse function is not physically realizable, just like ideal source, ideal resistors, and etc. It is very useful mathematical tool. The unit impulse may be regarded as an applied or resulting shock. It may be visualized as a very short duration pulse of unit area. This may be expressed mathematically as this one. And this figure below is an example of the unit impulse function. Next is the unit ramp function. This is 0 for negative values of t and has a unit slope for positive values of t. And this figure below is the unit ramp function. So now we will proceed to the step response of an RC circuit. When the DC source of an RC circuit is suddenly applied, the voltage or current source can be modeled as a step function, and the response is known as step response. The step response of a circuit is its behavior when the excitation is the step function, which may be a voltage or a current source. The step response is the response of the circuit due to a sudden application of a DC voltage or current source. And this figure below is an RC circuit with voltage step input. Now, I will be discussing the step response of an RL circuit. Consider the RL circuit in figure 748, which is the A, this one, which may be replaced by the circuit in figure 7.48, which is this one, the B. Again, our goal is to find the inductor current I as the circuit response and equations through 7.50 through 7.53. Let the response be the sum of the transient response and the steady state response, and we will get this equation. And this figure below is an RL circuit with a step input voltage. So step response of an RL circuit, we know that the transient response is always a decay exponential, that is this one IT and tau. We get this, which is 7.56. This is the formula where A is a constant to be determined. The steady state response is the value of the current a long time after the switch in figure 748A is closed. We know that the transient response essentially dies out after 5 time constants. At the time, the inductor becomes a short circuit and the voltage across it is zero. The entire source voltage, Vs, appears across the R. Thus, the steady state response is ISS is equal to Vs over R, this formula. Substitution, substitution, substituting equations 7.56 and 7.57 into the equation 7.55, it gives us this formula. We now determine the constant A from the initial value of I. Let IO be the initial current through the inductor, which may come from a source other than voltage, other than Vs, since the current through the inductor cannot change instantaneously. So we get this formula. Thus, at t is equal to 0, the equation 7.58 becomes this equation. I mean this formula or equation. From this, we obtain A as this equation. So substituting for A in equation 7.58, we get this equation here. And this is the complete response of the RL circuit. It is illustrated in the figure 749, which is this one, the total response of RL circuit with the initial inductor current IO. And it may be written as this equation. And where IO is equal to I infinity are the initial and the final values of I, respectively. Thus, to find the step response of an RL circuit requires three things. First is the initial inductor current, second is the final inductor current, and the third is the time constant.